Okay, this video is for some review over area between the curves, some volumes of revolution, and cross sections. So let's go ahead and begin this problem. This problem has a picture at the top, and it says, let R be the region in the first quadrant bounded by the graph of y equals 2 square root of x, the horizontal line y equals 4, and the x and the y-axis is shown in the figure. So we're supposed to find this area R. So I'm going to go ahead, since we typically like to do dx problems, I'm going to go ahead and place my rectangle so that it would be in a dx position. And we know that area between the curves is defined with an integral. And in this case, this region covers the x values from 0 to 4. So my bounds will be from 0 to 4. And the two curves we're looking at are y equals 4 and y equals 2 square root of x. When we find area between the curves, we always go with the top curve minus the bottom curve. So my top curve being 4 and my bottom curve being 2 square root of x, we will go ahead and set that up for minus 2 square root of x. And then we know we're doing this with respect to x, so I'll place a dx there. This is a non-calculator problem that we're working with, so we're going to go ahead and solve and compute this. So we will go ahead and integrate these parts. When we take the integral, it's doing the derivative backwards. So the derivative of 4x is 4 minus, we can just go ahead and use the rules for integration where we raise it by 1 and put it over that power. And then we'll be computing this from 0 to 4. So I now have 4x minus, this would be 4/3, x to the 3/2. And using fundamental theorem of calculus, we'll go ahead and place 4 in first for my x values. And then we'll place in the 0. So it's minus the second part. Placing in 0 is only going to just give me 0. So there's no reason to really write all of that out. We end up getting 16 minus, this would be the square root of 4 cubed. So this would be an 8 times 4/3, which would end up giving me 16 minus 32/3. I could make common denominators, so that would be 48 over 3 minus 32 over 3, which gives me the answer of 16 over 3. So the area between the curves is 16 over 3. Looking at the next part of this problem, it is asking me to write, but not to solve, the integral expression that gives the volume of the solid generated when R is rotated about the y equals 5 line. So I'll go ahead and place that line up here in red so we can start to discuss that. We're going to be rotating it about the y equals 5 line. Again, if we can do a dx problem, we want to go ahead and do a dx. So as I look at this, I'm going to determine what kind of shape I'd be getting. When I would be revolving this about the y equals 5, there is a gap right here that occurs, so there's a hole. So my revolution would actually give me a washer because of that hole right in here. So I'm going to be revolving it and I'll produce this hole. So this is a washer problem. So we know that washers are determined by the area of the large circle. We've already figured out that we can take out pi, and then we can integrate that from big R squared minus our small r squared. And again, we are going to be doing a dx problem here. So there's my area of my large circle, pi big R squared, that's the circle, minus pi little r squared. That's my little circle, so I'm subtracting away that part of the object. Big R be right here, Okay, so that's my large radius that I'm revolving. So that's this part. Big R will be defined as the top curve, which would be 5 minus the bottom curve, 2 square root of x. And my little r is right here. It'll be defined as 5 minus 4, which just ends up being a 1. So I'll come down here and place that in my integral. Big R squared. Big R was 5 minus square root of x, and that's squared, minus my little r was 1 squared, and I'll put my dx on the end. Now, since I do not have to evaluate this one, to only set it up, this is my solution. The last part of this problem is asking me to find the cross sections of the solid. So we have a region R, the same region, and it's the base would look like this. And that cross section is, again, we're supposed to write but not solve an integral that gives the volume of that solid. So this time, since it is perpendicular to the y-axis, it's actually a dy question. Cross sections we know are determined with integrals. So cross sections are done with integrals. Since we know this is going to be a dy, I'll go ahead and put a dy on the end. It's the integral of the area of the shape that's created. The area of the shape that's created is a rectangle in this case. So go more into detail on that in a little while. But this cross section would go from 0 to 4. That is my y bounds because it is a dy. Now this one just happens to be the same x bounds. So I'll make sure you guys understand that I really am using dy coordinates here for my bounds. So the area of the shape would be base times height for a rectangle, but it also tells us something about the height. So I'll go ahead and write up here that my rectangle is base times height, but we know that the height is actually 2 times the base. So that will be what I'm placing in here. I'm going to be doing base times 2 times base, and it will be a dy. So I need to figure out what b is. So b, a cross section, what it does is it takes that slice, the bottom of my slice, and what happens when it lays over on the side, it becomes a rectangle. So this is my base right here, and that falls right there. So my base, because this is a dy, will subtract the right-hand side minus the left-hand side. So if you remember, the right-hand side is actually the line y equals 2 square root of x. The problem with that is I need to put this in terms of dy, so I actually need to solve this one for y. So off to the side, or for x, excuse me. So off to the side here, I'm going to divide by 2, and then I will square both sides. And when I square both sides, I get y squared over 4. So my right-hand side, instead of using this one, I will actually be using x equals y squared over 4. And then my left-hand side is line x equals 0. So my base ends up being just y squared over 4 minus 0. My right curve minus my left curve. So just y squared over 4. So I'll finish this up down here, and I'll place y squared in for my base, times 2 times another one of those bases. Now at this point I could simplify this by taking out the 2 and this 16, so that would end up being 2 over 16 out front, which is 1/8, and then I'd have y to the 4th power here. I may very well just go ahead and simplify that, so it's 1/8, the integral from 0 to 4, y to the 4th dy. Now we could actually compute this, but since it says do not evaluate, I'll be done with this particular problem. So hopefully this has given you a little bit of reminder on area between the curves, volumes of revolution, and cross sections.